Hello geometry students, my name is Emigh, and this video is our discussion on chapter 11, surface area and volume. And we're going to cover two sections, 11.1 and 11.2. 11.1 is on solids and cross sections. A polyhedron is a solid. Think of those polygons we've talked about so much, but take it to a third dimension, so it's now a polyhedron. Its surface is made up of polygons. Each polygon is a face of the polyhedron. An edge is formed by the intersection of two of the faces, and a vertex is where three or more edges intersect. You can see from the figure there, faces, vertices, and edges. There was a mathematician, Euler, sounds like, or looks like it's Euler, but it's Euler's formula. And that is the sum of the number of faces, we're going to use capital F to represent, and vertices, we're going to use capital V to represent. So the sum of F and V, the number of faces and the number of vertices of a polyhedron, is 2 more than the number of its edges. So we have this equation here that we can use to find a missing count should we need to. Like right here. Says how many vertices, edges, and faces does the polyhedron at the right have, and then use your results to verify Euler's formula. Okay, so go ahead and check out this polyhedron. 1, 2, 3, 4, 5. It's 6-sided. So it's a hexagon face there, rectangle sides here. So we have a hexagonal prism, which we'll talk about more specifically soon. And in this hexagonal prism, or polyhedron, we have 8 faces, 12 vertices, and if you counted the edges correctly, we would get 18 edges. And so we're going to plug those in now to see if, in fact, V and F combined is equivalent to the number of edges plus 2 more. So we're checking if 8 plus 12 more is equivalent to 18 plus 2 more. And it is. So verifying Euler's formula there. Cross sections are the intersection of a solid and a plane. So imagine taking a polyhedron like this one you see here. This is a triangular prism, and cutting it with a plane. Okay, so a two-dimensional surface. So taking a three-dimensional solid and cutting it with a two-dimensional plane. What we get as a result is called a cross section. You can think of a cross section as a very thin slice of the solid. So you can see we have the plane here. Our solid is this triangular prism. And then this part in red, this part is called the cross section. Okay, so it's just a two-dimensional triangle in this one. Okay, let's practice describing a cross section. What is the cross-section formed by the plane and the solid shown? Assume that each plane is perpendicular or parallel to the circular base of its solid. All right, so check this one out here. We have a cylinder being cut by a plane, and the cross-section, what shape does that look like it results in? If you said rectangle, you got it right. Nice job. Try part B. If you said circle, nice work. This cylinder is being cut by this plane. The resulting cross section is right here, which is a circle. And we know it's not an oval based off this. In this, assume that each plane is perpendicular parallel to the circular bases. So that makes it a circle, not an oval. All right. Cross sections can be used in topographic maps. Sometimes called contour maps. So you can see we have this three-dimensional space, so this solid, and we're cutting it with these two-dimensional planes. And then what we can do with that information is turn it into a contour map, so a two-dimensional map like you see here. So each of these represents a cross section, so where the solid is cut by the plane. It's cut 1, 2, 3, 4 times, which is why you see 1, 2, 3, 4 cross sections there. Okay, the number on each cross section represents the vertical height. And so that provides us all the information from this solid being cut by planes in a two-dimensional contour map. So to read a contour map, this one, for example, we have the elevation in meters. And so let's check out if Ace or Bunker Hill has a greater elevation. Okay, remember to look at the numbers. Those show the vertical height or the elevation. Looks like we've got 40 for Bunker and 50 for Ace. So which one do you think? Does Ace or Bunker Hill have a greater elevation? And if you said Ace with an elevation of 50 meters, you got it right. Bunker Hill is only 40 meters in elevation, which is read on a two-dimensional map. Where is the landscape the steepest? Something else we can get from the contour map is seeing where the elevation changes the fastest. So for this one, look at the west side of Ace Hill. Okay, so Ace Hill is right here. So focus on Ace Hill right here and the west side, so over here. See how the west side of Ace Hill is the steepest since the contour lines are the closest together. So these lines are super close together, which means the elevation is changing from 10 to 20 to 30 to 40 to 50 meters in a steep fashion over there. Whereas let's say if you wanted to climb Ace Hill and you wanted like the least steep route, you would want to climb like over here, where the contour lines are further apart. That means you can travel from here to here, and it's only a 10-meter raise, and then 10 meters, and then 10 meters, and then 10 meters, versus only traveling this far, and you're up 10, that far is up 10, that far is up 10, and that far is up 10. Rotating a solid. Try to visualize rotating a plane region about a line. What is the end result of rotating a rectangular region about the line L? All right, here's our visual. We have a rectangular region right here, and we have line L right here. Okay, so imagine taking this rectangular region and almost just like flicking it with your finger and it's spinning around. What solid do you think it would make? If you said a cylinder like this, you got it right. And that would be the result of rotating a solid. And the end result is a cylinder. Okay, notice that a cylinder has what we call rotational symmetry. We often talk about line symmetry, like if we were to take this isosceles triangle and we were to cut it in half, or to bisect this angle here and bisect this side, then we have line symmetry. We could fold that triangle about that line and it'd be the same on both sides. But here we're talking about rotational symmetry. And a cylinder is a solid of revolution. We can call it that. We can call it a solid of revolution because it is the solid produced by revolving or spinning a plane about a line. All right, what do you think of this one? Describe the solid of revolution obtained by rotating this triangular plane about this line L. If you said that that solid of revolution is a cone, then you got it right. Nice job. 11.2 is on surface area of prisms and cylinders. Okay, so we're going to start by looking at nets and surface area. So surface area, we're going to use a capital S, capital A. You guys need to remember that, okay? Not lowercase s, not lowercase a. We're going to use capital S, capital A. The surface area is the sum, that means add them up, of the areas of the rectangles. So remember, area follows the rules of addition. So if we just take the area of each of these little rectangles and we add them up, then we'll have the entire surface area. So what you see here is this solid right there. It almost looks like, maybe think of a shoebox. If you were to unfold this shoebox, it would result in a net. Now, you may unfold yours a little differently than this one's unfolded here, but it doesn't matter. If we unfold our shoebox correctly and don't make a mistake, we will get the same surface area for that shoebox by adding up the area of each of the rectangles. So instead of going one by one with these rectangles, we're going to break it into, that one right there is 6 square units. This one right here is 12. This is a 6 by 3, so 18 square units. This 2 by 3 has 6 square units. This 6 by 3 has 18 square units. And lastly, this rectangle, this 6 by 2, has 12 square units. So if we add all those up, 6, 12, 18, 6, 18, and 12 more, we get 72, which means that this shoebox right here has a surface area, just the outside, just like the cardboard portion of the shoebox, has a surface area of 72 square units. And remember, that's not linear units. Square units are each of these little squares. It would take 72 of those to wrap your shoebox in wrapping paper, if you want to think about it that way. Okay, so look at this prism, and we're asked to find the surface area, so capital S, capital A, and we have other formulas to find surface area, but for now we're going to practice with using a net. So if we unfold this, it's a rectangular prism, then we end up with, well, one possible net looks like this here. Your net may look a little different, and that's okay. Then if we take the sum of each of those rectangles, add them up, we'll get the surface area. So one at a time. The top one is 12 square units. This one is 20 square units. Another 12 square units. 3 by 5 gives us 15. This is another 20, and this is another 15. Adding all of those up, we get 94. So it turns out the surface area of this rectangular prism is 94 square centimeters. A prism is a polyhedron with two congruent parallel faces. Those congruent parallel faces we are going to refer to as the bases. Okay, it's very important that you guys remember that, because our formulas are going to be dependent on like the area of a base. So you have to know, well, which one is the base? So when you look at this right here, when you look at this prism, it's got multiple faces. It's got a top, a bottom, and then 1, 2, 3, 4, 5 around. But the ones, if they say bases, you have to find the two that are parallel and congruent. And that would be this top pentagon and this bottom pentagon. So we're starting to get more specific with our names here. The top and the bottom parallel congruent bases, or faces, are called the bases. And it won't always be top and bottom. If we just, went over and pushed this thing over and it fell on its side, then it's not as obvious that those are the bases. But you have to remember the definition of the bases of a prism, which is the two congruent parallel faces. All right, we also have lateral faces, and those would be the remaining 1, 2, 3, 4, 5 rectangles going around the two congruent pentagons. All right, here's another example. This right here is called a triangular prism. Of all the faces up there, only 2 are congruent and parallel, and that would be this triangle and this triangle. Therefore, they are the bases. The others, the rectangles, are the lateral faces, and then we also have lateral edges. All right, the lateral area. For lateral area, we're going to use capital L, capital A. Lateral area of a prism is the sum of the areas of the lateral faces. Okay, notice that does not include the bases. The surface area, capital S, capital A, is the sum of the lateral area plus the area of the two bases. So, One way to explain that might make more sense is if you're trying, let's focus on this one right here first, okay? Focus on that one. If you are wanting to paint or wrap just the rectangular parts, just the surrounding part, maybe wallpaper, that is the lateral area, just the surrounding part. Think of wallpaper maybe. That's a room if you're standing inside of it and you're just going to wallpaper the walls. You're not going to wallpaper the ceiling or the floor. What you're doing, you would have to calculate your lateral area to know how much wallpaper to buy. Now, if you're going to do the whole surface, so that was lateral area, just the walls. If you're going to do the whole surface of the room, so surface area, you've got to do the wallpaper for all the lateral faces, plus sign the area for the two pentagons, the two bases. Okay, so it's really important that you guys keep straight what LA and SA represent, because we're going to have exercises where you're asked, find the lateral area, find the surface area. So you not only need to know what they mean, but you also soon will get some formulas for them. Okay, a prism. An altitude of a prism is a perpendicular segment that joins the two bases, okay? Its length, so the length of that altitude is called the height. You guys have seen this before. You've seen base times height many times, like in two-dimensional stuff. Like this, maybe you'll identify this is the base, and therefore this would be the height. So don't lose grasp of that knowledge. You know that. We're just now taking it into a three-dimensional polyhedron, or a solid. Okay, so for when you're talking about a solid, a prism has an altitude, okay? The length of that altitude is what we call the height. And that height, or that altitude, is the distance between the two bases. So this top one is base, I'll put sub T for top, and down here is a base, sub B for bottom. So the height is the distance between the two bases. It seems obvious in this one because, like, the orientation of that prism, it makes sense that that's the height. But what I want you to do now is focus on this one. When you look at this one right here, it's easy to go, oh, the height of this would be this distance. And I mean, that makes sense. I get it. If you walked up to this solid with a tape measure, that's what you would measure as the height. But when applying the formulas, that is not the altitude. The height, or the altitude, the definition of that is the distance between the two bases. So what we need to do is identify the two bases. Okay, well, of this right prism, we have 1, 2, 3, 4, 5. We have 6 faces. Only 2 of them are congruent and parallel, and that would be this trapezoid and this trapezoid there. Since those are the bases, I'll call this one base sub 1 and this one base sub 2. Since those are the bases, then the height is this segment right here, the distance between those two bases. All right, so be careful when you're applying a formula and one of the blanks or variables is the height. Be careful that you identify the height correctly as being the distance between the two bases. Oblique prisms are where the height is on the outside of the prism. So right here, the two parallel congruent bases are the 2 that I just highlighted, making this the altitude. And if that is the altitude, then the height is its length, okay? And it's on the outside because it's an oblique prism. Okay, surface area of a prism theorem. The surface area, SA, of a right prism, so remember the right prism, that's these ones, okay? Surface area of a right prism is 2 times capital B plus sign, capital P, lowercase h. Okay, so that's quite a few variables in that. That's SA equals 2B plus PH. Well, what do those letters stand for? Capital B is the area of the base, It's not a length. It's in square units. It's an area. Capital P is the perimeter of the base, and that's in linear units for perimeter. And lowercase h is the height of the prism, right? So capital B, area of the base, capital P, perimeter of the base, lowercase h, height of the prism. Not of one of the faces. It's the height of the entire prism. Okay, so that is this formula here on the very bottom of your screen. SA equals this. The lateral area, you would just take off the bases. Remember, lateral area is just like wallpaper in the walls, not the ceiling and the roof. I'm sorry, the floor and the ceiling. So to get lateral area, just cross off the two bases, and there you go. You've got lateral area, which is capital P times lowercase h. All right, I suggest you guys write these down. Their development you can see here from going from a solid to a net. So I suggest you write those down right there. I also suggest that you write down what capital P stands for, which is written for you right there, what lowercase h stands for, which is right there, and what capital B stands for, which is right there, okay? All right, so let's use formulas to find surface area this time. So we're given a prism, and we're asked what is the surface area of the prism rounded to a whole number. All right, we're going to start by identifying the formula that we're going to use. We're being asked to find the surface area, capital S, capital A, of this right prism, which means our formula is 2, capital B, plus capital P times lowercase h. All right, what I like to do now is turn this into a blank template. And I'll just go for one blank at a time. Okay, capital B stands for the area of the base. Well, of the 5 faces up here, which 2 are the bases? And the answer is the 2 triangles, because those are the congruent parallel sides. So for capital B, I need to find the area of this triangle right here. And there are 2 of them, but the formula takes care of the 2 for us. So the area of that triangle, let me twist it a little bit. Having trouble seeing it in this 3-dimensional orientation. 3 would be here, 4 would be here. That's a Pythagorean triple. 5 would be there, although we don't need that for the area of that. So capital B is equivalent to 5, 1/2 base times height of this little triangle, not of the prism. Okay, so 1/2 base is 4, height is 3, and half of that. So that's 12 divided by 2, which is 6. So our first blank is a 6. And that's square centimeters if you'd like to write your units in your formulas. Capital P, that is the perimeter of the base. Okay, perimeter of the base is really hard to find if you don't know what the base is. So, I mean, we just talked about it, but here we go. If you didn't follow, we're going to say it again. To identify the base, you look at this solid, this triangular prism, and you find the 2 faces that are congruent and parallel. And that is the triangles. So capital P is the perimeter of that one of the triangles. Oh, so it is good that we identified this as the Pythagorean triple, because to get the perimeter, we do need the length of the hypotenuse. So capital P, or the perimeter of the base, is 3 plus 4 plus 5, 12. So our second blank is 12. Third blank, lowercase h. That would be the height. And, oh, we got lucky this time. They gave it to us. The distance between those 2 triangles is 6 centimeters. So 6 there. Okay, let's... if we do 2 times 6 plus 12 times 6, then we get our surface area is equal to, and that was an 84. I'll erase my writing and show that typed up in just a second. So we end up with 84, and its surface area, so it's square centimeters. Okay, I'm going to erase my writing, and there we go. The surface area of the prism is 84 square centimeters. Cylinders, those are a solid that have two congruent parallel bases, but those two congruent parallel bases this time are a very specific shape. They are circles. So think of a can of soup, if you will. The altitude of a cylinder is the same as before. It's the perpendicular segment that joins the planes. So this time the planes of the bases. So this time it's the perpendicular segment that joins the circles. And that's lowercase h. And in a right cylinder, the segment joining the centers of the base is an altitude. And in an oblique cylinder, the segment joining the centers is not perpendicular to the planes containing the base. So it's on the outside here. So we have right cylinders, we have oblique cylinders, and they are just like our prisms, except that their bases are circles. Okay, so to find the surface area of a cylinder, we've got to apply our formulas involving pi, because the base is a circle, and we know that area and circumference of a circle involves pi. So if you recall, let's pretend this is our base right there, or it is our base actually. So if I were to ask you, what's the area of that circle right there? You would say, well, the area of a circle is pi r squared. And what if I said, well, what's the perimeter of that circle? Well, we wouldn't actually use the word for perimeter when we're talking a circle. A circle has a very specific name for its perimeter. It's called the circumference. And circumference, you guys know, is 2 pi r. So that is why, since our surface area is dependent on 2 capital B's plus sign, capital P, lowercase h. It's the same here. That's 2 capital B's, there's capital B for you, plus 2 pi r, that's our capital P, and then lowercase h. So it's the same thing, it's just involving pi because our bases are circles. And you can see the development of that surface area formula by taking this solid and unfolding it. It's almost like taking the label off of a soup can and then taking that soup can, measuring the lid or the bottom of the can. Those are the bases. So you'd measure its area, you'd measure its circumference, and then the height of the soup label is the height of the cylinder. And then you have everything you need to derive that formula and apply it. Okay, let's try it. The radius of the base of a cylinder is 4 inches, and its height is 6. What is the surface area of the cylinder? Now they want it in terms of pi, so they want the exact surface area. What that means is do not use your pi key, okay, on your calculator. Don't use it. All right, they want our answer in terms of pi. Let's draw a picture. The radius of the base of a cylinder is 4 inches. So a cylinder, you want to draw like 2 squished circles. You want to try to make them parallel and congruent. Attach them just with 2 lines, even though they're attached infinitely many times, because a circle has infinitely many points on it. The radius of the base, so that would be right here, is 4 inches. And the height is 6, that would be this right here, inches. What is the surface area of the cylinder? Okay, so let's see if we have everything we need. We set our formula up first in its general form. I highly suggest you write the formula in its general form first. Then turn it into a blank template. 2 remains 2, pi remains pi, r needs to be plugged in, plus sign. 2 remains 2, pi remains pi, r needs to be plugged in, and h needs to be plugged in. So we have 3 blanks. The first 2 are the radius of the base, so 4 and 4. And the third blank is the height, which they gave us everything we needed for this one. That was nice. 6. Okay, from here you've got to do some simplifying. Order of operations is focus on this term and this term separately. So ignore that plus sign for a little bit. 4 squared is 16 times 2, that's 32 times pi, plus sign 2 times 4 times 6, that is 48 pi's. Now looking at those two terms, they are like terms, which means we can combine like terms. And if we do that correctly, we will get 80. Let me erase that stuff first. 48 and 32 is 80. Yes, good. And that's 80 pi's. Be careful, it does not become 80 pi's squared, okay? 32 pi plus 64 pi is 80 pi. 1 pi plus 1 pi is 2 pi. Pi only becomes squared if you're talking multiplication, like pi times pi is pi squared. But this is addition, so it remains pi. So we have 80 pi square inches. Units are squared, pi is not. Okay, I'm going to erase my work now and put that up typed so it looks a little nicer for you. There. So 80 pi units are square inches. All right. I want you to go ahead and pause this video and read this one carefully. Well, let's read it together. Standing 82 feet tall with a radius of 11 feet. So radius 11, 82 feet tall is located, approximately 11 feet. The Aquadome is located in the Radisson Hotel in Berlin, Germany, and is titled the world's largest cylindrical fish tank. Find the surface area of this tank without the area of the top base. Okay, so be careful here. It wants the surface area, but it doesn't want the top base because for some reason, maybe, I don't know why, but we don't want the top base, so not this one here. So we're not going to use 2 bases, we're going to use 1 base. So be careful, think about that. And then it says find the exact surface area and then also approximate it to the nearest tenth. Okay, pause this video and try that now. Welcome back, let's see how you did. If you set up your formula as surface area equals 1 capital B's plus the perimeter times the height, you're on the right track. That would be pi r squared plus 2 pi r h. We need to plug in r and h, and luckily they gave us both of those. R is 11 and h is 82. So right there, the blanks have been filled in. 11 are the variables, 11, 11, and 82. Okay, now we're really careful. Order of operations gives us 121 pi plus 1804 pi. Those are like terms, so we combine like terms to get 1925 pi. And if we put square feet, that right there is called the exact surface area. But it also wants us to approximate to the nearest tenth. So pick your calculator up and you're going to type in 1925 times and use the pi key. Don't use pi as approximately 3.14 unless the problem says it's okay for you to do that. And on your calculator, if you got approximately 6,047.6 to the nearest tenth square feet, you got that right. That will conclude our discussion on 11.1 and 11.2. My name is Jami Emigh. Thank you for joining me, and I'll see you next time for our discussion on section 11.3.